So last time we talked about searching through a graph where we were trying to minimize the number of actions we took. That was, we thought of each possible state as a node in a graph, and each action was an edge that would take us from one state to another. They were all equally weighted, so we were just trying to minimize the number of actions to get from the initial state to one of the goal states, right? Now we need to talk about when the edges have a weight associated with them. So for example, when Google Maps recommends a route to you, you can think of every intersection on the map as being a node in a graph. And that maybe they're trying to minimize the time from here out to, let's see, Fat Matt's Rib Shack. And so it would look at all the possible paths, and it would have a weight for how long it typically takes to get from here to there at this time, and how long it takes to get from there to there at this time, and that way, what it's trying to do is minimize the total amount of time for the whole journey, right? So for each edge, if you can find a series of edges that take you from this initial state to the goal state, there's probably a lot of different routes, but you're going to be looking for the one with the shortest cost. That is the sum of the costs associated with each edge. So maybe it's distance, maybe it's time, maybe it's price, right? Is that you're using mass transit and you're trying to minimize the amount of money you're spending on your bus fares. Make sense? There's several different methods for doing these, and this is probably the map problem is the sort of canonical case, but there's actually a lot of different problems that are in this space. So this is sort of how I tend to think of it, right? Is we have the initial state. You're in Yonkers. You'd like to get to the JFK airport. There's a couple of different routes. You can go through Penn Station. You can go through Howard Beach and on to RFK, or you can go to Jamaica and then JFK from there. And what you do is you start at this state, and then you're going to expand out the different actions you can take, whether that's going this way or that way. And you're going to be keeping track of the cost. And the game is, how do we find the cheapest route to the eventual goal? Good? All right. Same, very similar definition to last time. That is, we have an initial state. We have a function for testing whether a state is a goal state. We have a set of actions. Well, so a function A that returns a set of actions available at any given state. And here's the difference. The difference is for function T, which says if I'm at this state and I'm taking this action, not only does it give you the new state, the next intersection, the next city that you're getting to, but it also gives you a cost. That is, what is the cost of taking this action in state S? Okay? And for now, we're going to assume that cost is greater than or equal to 0. A lot of the really elegant stuff that we do breaks down if cost can be negative. So maybe you've bumped into Dijkstra's algorithm already. There are methods that deal with negative costs, but honestly, in the real world, most problems have a 0 or greater cost. It's very rare that you get paid to take the bus from here to there. It always costs to get somewhere on the bus. Maybe 0, but there's usually a cost. So let's assume for now, as I'm going through these slides, that the cost on any of these edges is at least 0. And you could use breadth first search, right? You could use breadth first search, and it would actually give you the correct answer if all your links had the same cost, right? We can think of breadth first search as each edge has a cost of 1, or in this case 4. And if you do breadth first search, you're gonna the first time you pop JFK off of the stack, you will have found the shortest path to JFK. How can we sort of extend the idea of breadth first search to deal with actions that have different costs, edges that have different costs associated with them? And that's uniform cost search, UCS. This is very similar to Dijkstra's algorithm. I'll spell out the differences when we get to the end. But the idea is that we're going to use a priority key. And so we're always going to keep the one that is the cheapest unvisited state always at the front. So we'll start off in Yonkers. To get from Yonkers to Penn Station is going to be, the first time you see it, it's going to be $6.50. But then you figure out that if you go to Yonkers through Jamaica And then you go to Penn Station. From that, now it's $5.25 to get to Penn Station. And then $3 more here. That's cheaper than the $6 here, and so on. Here's the priority queue that we're going to use. So we're always going to be able to say either insert or decrease. So here's the value going in, and here's the priority. There's a couple of different possibilities. The first one is this value is already in your priority queue, in which case you're going to check to see what is the current value of it in your priority queue. And if this one is lower, that is, this one would move it forward closer to the front of the queue, then we're going to update it. We're going to give it the new priority and return true. Yes, I had to change the location that it was sitting in. If the priority is greater than or equal to, we're going to return false. I didn't have to make any changes. You telling me this didn't do anything. If it is not inside the priority queue at all, we're going to insert it with that priority. Everybody okay with that definition of a good method for insert or decrease the priority queue? Notice that it returns a Boolean, which tells you if things had to get updated in this queue. Once you have that, we can actually give the code for the uniform cost search like this. We'll start off with the backtracking map. So as we're going, we're always going to be keeping track of what is if I had to go backwards from this point back to the initial state, what would be the cheapest way to go back? So we got this map. We'll keep a set of everything that we have already visited. And then we'll create this priority queue. And we'll insert the first state in. And the cost of getting to the first state is 0. And now while there's something to pop out of this queue, so this is the state and the cost it takes to get there. If this is the goal, then we can just return the backtracking from there. Otherwise, we'll add it to the list of things that are visited. Then we'll go through all the actions you can take in that state, and we'll compute what would be the next state from here if I took that action, and how much would it cost to get from S to S prime, that's C prime. We know how much it costs to get to S, that was C. So to get to S prime through this route would be C plus C prime. But we may have already found a route to this location, right? Just like in this example, if I looked at Penn Station first, so I think it cost $6.50 to get there. But if I go look at Jamaica next, and I go back and I look at this, I'm like, oh, I found a cheaper route to get from Yonkers to Penn Station than I thought before. So if I end up changing it, that is, I insert it or decrease it, that means I have to update the backtracking table with the new previous state and the new action that would get you there. Yeah? And you go on through this, and the first goal you reach, the first one that satisfies your goal, then you deal with that. If you never reach the goal and you run out of things in the queue, you return failure. There's a lot of sort of interesting, yeah, there. I'm sorry, say real loud. If this one is visited, continue. Yeah, you'd skip everything in the for loop and you go to the next action. Why is that? Because the first time that you pop a state off of this, the first time you pop a state off, that is going to be the very shortest route. So you could imagine that maybe there's some really long route back to Penn Station, but after you pop Penn Station off, that means that was the cheapest possible route. How do we know that? What's happening is we're popping things off this queue based on the cost it took to get there. So it is a monotonically increasing thing. It will never decrease. Every time you pop something off, its distance, its cost is slightly more than or equal to the one that you popped off beforehand. It's never going to go down. So if I've already seen it, I've seen a cheaper route. If I've already seen it in the sense of popping it off the stack here, I've already seen the cheapest route to get there. And that's one of the nice things about Dijkstra's algorithm and uniform cost search is because we're always popping things off based on this priority queue. It's the first time it pops off, that's the best. Yes. If this cost is a cheaper route than we have seen before, the state will get moved up in the priority queue.
Oh, so we're just like describing convenience already. Four or five.
Yeah, so but the first time we put it in the priority queue, it may not be the best route to it. So as it's living in the priority queue, we might keep finding better routes to it, and we'd be moving it up. And each time we move it up, not only do we move it up in the thing, but we also have to update the backtracking table to say, okay, now this is the cheapest route that we've seen to state S prime. Not the first time we see it. This is not necessarily the cheapest route. It's when we pop it off the queue that we know that's the cheapest possible route. Is that all right? Okay. Yeah, we'll see it twice. Once when we're putting it on the queue and once we're popping it off. The time we see it pop off the queue, we know we have the shortest route. Is that all right? This is kind of deep. Note that things go in the backtracking table before they are visited. That is, you add them into the backtracking table the first time you see them. So this one has been explored, and so this node is in the backtracking table. These ones that are in the visited set, I know that I have already found the cheapest route to them. And these ones I know about, but I'm not certain that I have the cheapest route to them yet. It's only later when I pop them off that I can be confident I found the cheapest route there. Questions on that? All right. We have the same idea of backtracking. I changed it slightly in this, but we'll backtrack, we'll create a list, and then we'll push the actions as we see them when we're going backwards from JFK to Howard to Penn to Jamaica to Yonkers. We're going to keep pushing the action that gets us there to the front of the queue. So we have to backtrack, but of course, the result we want to work forwards. Same as last time, really. Remember that when I did the breadth first search, I said we can actually sort of short circuit this. And instead of putting something in the queue, if we know it's a goal state, we'll just proclaim that we have found the route at that point. Yeah? And it was really tempting to think, could we do that in this case? And the answer is no, because as it's living in the queue, we could be finding quicker and quicker routes to get there. So it's not enough to have seen that the first time we see it, we don't think it's not necessarily the shortest route. It's only when we pop it off the queue that we can be confident that that is the shortest route. So we have to wait until the goal node is actually popped. Now, why don't we need to wait until we popped every node, right? Maybe in some world, we have to go through every route because possibly it could loop back and come back in a very short way. Well, the fact is that the uniform cost search, once again, because it's monotonically increasing, the cost of the thing popping off the queue, if it's popped off, that's the lowest cost to get there that's possible. It's ever going to happen. It's only going to be more expensive or the same. So we don't have to wait until we popped every node. We just wait until the goal node is popped off. That's the termination condition. In a lot of these search problems, this is the termination condition is the part that makes my head hurt. Is how can I be confident that I've found the shortest possible route? And this one takes a little bit of thought about why don't we have to pop every node? Okay, questions on that? Uniform cost search. So at this point, if you've taken 3510? 3510, you're saying this sounds a lot like Dijkstra's algorithm. And it is. This is exactly the same as Dijkstra's algorithm, except for one thing, which is Dijkstra's algorithm is sort of defined that from this initial node, I'm looking for the cheapest path to every possible node in the graph. Whereas when we're talking uniform cost search, when we get to the node we want and we pop it off the queue, we're all done. We don't care about the far frontiers. We're really just worried about path from A to B, whereas Dijkstra's is A to anything. Okay, so that's the difference. But they are the exact same algorithm. They just with Dijkstra's algorithm, you don't terminate. You just go until all the nodes have been popped off the queue. Okay. Questions? All right. Here's the thing, though, is that uniform cost search can be really slow. it searches in all directions for the cheapest possible node in all possible directions, the cheapest next node. So if you're in Yonkers here and you want to go to JFK, well, there's a whole bunch of cheap cities out there, Newark and Hudson and Red Hook. You can get these really cheap and you can explore these and you'll explore all this stuff. You're always looking for what is the next cheapest city to get to. And that's what comes off the queue. And gradually that visited set expands in sort of a circular manner if you assume that cost is the same as distance. So you get sort of this circle expanding out. And it has no real preference for any particular direction. Whereas if you're in Yonkers, it doesn't make sense to go all the way out to New Paltz up the Hudson if you know you want to go to JFK. So this is the wrong direction. So what we'd like to do is use that idea of a heuristic, that we want to be able to guess what's going to be close to the goal and tend to prioritize those. Yeah? So we talked about this last time, the idea of a greedy algorithm. And the idea that if you have two things sitting in the queue, you would pick the one that is closest to the endpoint. That's more likely to get you a quick answer. So in the case, Istanbul Air often has these really cheap flights. So maybe you get from Istanbul to JFK for $1. But getting from Yonkers to Istanbul is actually really expensive. But if you started here, you push both of these onto the queue, now this is the most promising one. So clearly greedy is kind of weird, right? Is that it ignores the cost of everything up to that point and just grabs the one that is the closest to the end. Right? Is that clear why greedy is not good in this case? If you're here, you push both these on the queue, you say, oh, well, this one is closer than that one, closer to the end, so I'm going to expand this one first. So instead, what we'd like to do is not just consider how expensive it is to get from the city to the end, but also include how much did it cost to get from Yonkers to Istanbul. Now, this is a really simple case. So usually there might be a whole bunch of nodes in between here and here and here. And so instead of knowing the exact price of getting it from Istanbul to JFK, we would make an estimate. We'd make a guess. We'd use a heuristic to guess what that would be. But we still would have the problem of we don't want to use just the guess from here to there. We want to use the sum of the whole route. We could, because we've worked our way from Yonkers to Istanbul, we know the exact cost here. But from here to here, we can only guess. But what we're going to do is we're going to add together the amount that took us to get to Istanbul and our guess of how much it's going to cost to get the rest of the way. And that's what we're going to use for priority. Oh, here's a fine example of greedy search gone bad, right? If you were here, start here with an initial, you pop both of these on into the priority queue. This one is closer to the goal physically than that one. So you would think, I'll expand this one first, and that would expand this one, and that 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 one, and this one, which is a terrible route. And then the next thing you would do is you'd start expanding that one, and then that one, and that one, that one, that one, that one. And the last possible thing would be the thing where you check the direct route. So instead of doing greedy search, we're going to set up our frontier. So the book talks about the frontier a lot. We talk about the stack and the queue and the priority queue where things are waiting to be expanded. That's what it refers to as the frontier. And so we do breadth first, we're talking about a first in, first out queue. When we do depth first, we're talking about a last in, first out queue, a stack, right? With uniform cost search, the priority is the nodes that are cheapest to reach from the initial state. And then we can do best first, which is priority is nodes from which we think it is cheap to reach the goal state. But instead of using any of these, what we're going to use is the sum of the two. So we're going to use, for Istanbul, for example, we're going to use the actual cost that it takes to get to Istanbul, and then some sort of a guess of how much it's going to cost to get the rest of the way to JFK. And that's going to tend to prioritize routes that are here and naturally in between them. This is called A-star search. People done A-star search before? Yes, no? Some have? Okay. It's a pretty common algorithm because it's actually pretty slick because it combines the speed of the greedy degree search with the sense of I know when I've got the best possible route from the uniform cost search. So we need to get to, we've gotten to sub-state S, like we've gotten to Hogan from Rockport. So we know how expensive that is. We had to step from here to, well, let's do a different example. We'll go Rockport to Tinville. We know how much this costs because it takes 13 kilometers from there to there. Yes? We have some heuristic that lets us estimate how far we think it's going to take to get from Tinville to Pinello. And in this case, the heuristic was 15. I guessed it was going to take 15 kilometers to travel from Tinville to Pinello. How did I do that? Well, I just looked at the longitude and latitude of this city and the longitude of that city. I used the Pythagorean theorem, and voila, I got a reasonable guess at the distance. So I didn't have to go through 1,000 cities. I just used longitude and latitude and got a calculation. So I have this heuristic. It's going to take 15 kilometers of travel to get from here to there. It's not actually right, because if I go from Tinville to Pinello, I may either have to go through Smithton, which would be 16 kilometers, or I need to go to Hogan, which would be 23 kilometers. So this is an optimistic estimate of the distance to travel from Tinville to Pinello. It's lower than what it would actually be. Yeah? Okay. But then what I'll do is I will take the actual distance of 13, and I'll take my guess of 15, and I'll add those together, and I get this number, which is sort of my guess at what is the distance from Rockport to Tinville, using the actual distance to here and the guess from there. Yeah? Go ahead. Yeah, so the heuristic, where does it come from? So on maps, it's kind of easy because we can use the longitude and latitude. So I know the longitude and latitude of these two cities. I can calculate it without doing a whole lot of graph search. But in these problem spaces, there's always a game of trying to figure out a good heuristic. Okay, and I'll give you the punchline, which is that an optimistic heuristic is the best. Heuristics that tend to underestimate the actual cost work really beautifully. And I'll tell you why, probably on Thursday. Yeah, so we're going to use this combination. G is the actual distance to get to a particular state. H is the heuristic distance to get from that state to the closest goal state. And then we'll use this sum, G and H, to prioritize the search, and that's called A-star search. Yeah? Let me show you what they look like first, and then we'll go back. So this is a homework assignment that I have done other semesters, but I have only so many exercises I can give you in a semester, so you don't get to do this one. I'm so sorry. But what it looks like is the students implement these different searches. So if I do the uniform cost search, you'll see that there is two cities. One is on the left. Where is it? One is on the left here. It's round and orange. And then there's one on the right that's over there. It's got green around it. The uniform cost search, you can see, is going out in all directions equally. And then eventually, it finds the city, and it has found the shortest route there. I couldn't say that was the best until it had been popped off. So it wasn't just when it got pushed on, it was when it got popped off. The frontier, that is, things that are in the backtracking table but are not yet in the visited set, that's what's in yellow. So I'm going to do it for you again. And you missed the beginning again. There it is. So the yellow ones are in the queue, and then once they've been expanded, they turn orange. And you can see it tends to go out. Once again, I used sort of longitude and latitude to estimate the distance. Actually, each connection has a distance that could be slightly larger than the Pythagorean theorem would give you, which tends to be true of roads in general, is that they're not perfectly straight. So if you use the Pythagorean theorem, you get something that is either equal to or less than the actual length of the road. And that's what I've got here, is each road could be a little bit more than its Pythagorean distance. Cool? So that's the uniform cost search. Let's see what it looks like when we do the exact same search, but we use the A star instead. And what we're hoping is that instead of it going out in a perfect circle, that it will tend to search things that are in the direction of the goal first. And you can see that's what it's doing, is it's not really tending to search up in the top and the bottom. It's tending to stretch out to the right towards the target there. Yeah? Okay. And then just for fun, let me show you a couple of the other ones. We can do a bidirectional uniform cost search. So this is just like bidirectional search, but it's uniform cost search going in both ways. So it starts at that city and has queues and backtracking tables in both directions. And then it's looking for places where it meets. And when it meets, it declares that's the best possible route. Yeah? But uniform cost search, once again, tends to go out in all directions equally. So it's making nice circles out in both directions. But because it's doing it bidirectional, it still saves you some time. But what about the best possible combination, which is actually a little bit tricky because, well, here we go. This is the bidirectional A star search. So in this one, you can see they're already reaching out toward each other. This is these search contours, and there it found them. This is can be a little bit tricky because getting the termination criteria right is trickier than you would think. I'll be happy to share the code with you if someday you need to implement it. All right, so that should give you a little bit of an intuitive feel of why we prefer to use A star rather than uniform cost search. Uniform cost search is theoretically beautifully, but it tends to expand a lot more nodes than if we use A star, where it tends to lean towards the target. Of course, that means that for A star, you need to come up with a heuristic. And the heuristic is really often the most tricky part, is trying to find a heuristic that is really quick to calculate, right? If it takes a long time to calculate the heuristic, it doesn't save you any time. And then also is kind of accurate, right? Is that things that are close to the goal state should have smaller values for the heuristic, so that it actually tends to go straight to the target. You can imagine the stupidest heuristic, right? The stupidest heuristic is it just returns 0. I always think that I'm there. And if you do that, you get uniform cost search, right? Is that the two algorithms are the same, except we prioritize it based on the sum of the two. And if the heuristic always returns 0s, you're always prioritizing just based on how much it costs to get where you are. And that's uniform cost search. So the smarter your heuristic is, the faster your search tends to be, in the sense of you are expanding fewer nodes. And so here's the algorithm. Same idea. We got a priority queue and a backtracking table. We're going to insert S0. You could do the value. It doesn't honestly matter, because when it gets popped off the queue, it's the only thing in there. So I said, well, let's just say I want to put 0 plus a guess of how much it's going to cost to get to the goal node. I'll insert that into the queue. I've got the backtracking. There's no state and no action beforehand, and it costs 0 to get there. I'm going to start popping things off of this priority queue. If it's the goal, I've found it, and I can do backtracking from there. If it's not the goal, I can actually look it up in this backtracking table where I put the actual distance, the cost to get from S0 to S. That is in the backtracking table with these other things. In this case, it was 0. We'll call it G because that's what we always call it, G. Don't know why we always call it G. It's G. That's the actual cost to get from S0 to S. And then we'll go through all the children. And for each child, we'll figure out what is the next action. We'll go through the actions. We'll figure out what is the next state and what is the cost to get from S to S prime using that action A. We can create the actual cost to get to S prime through this route is G plus C prime. Now, we may have already found some route there. So first thing is, if it isn't in the backtracking table, or the cost to get there is cheaper than the cost that is already in that table. That make sense? These are the terms under which I have to update my guess about the cost to get to S prime. So if I've never seen it before, I definitely have to update my belief about how much it costs to get there. And if I've seen it, but this notation is a little funny. This is the number 2 item in the trio. So 0, 1, 2. This is the actual cost. It's art that's in the table. Then my new estimate is going to be the cost plus the heuristic for my cost of getting from S prime to the goal state. And then I will insert or decrease it in the priority queue. And if I had to insert it or decrease it, then I will update its value in the backtracking table. Should there be an if there? I was just looking at that. Should there be an if there? I have the colon, which means that when I was writing it, I was probably thinking of an if. But I didn't put an if and I didn't insert it, didn't indent it. So what was I thinking? All right, if it's not in the table, then this is definitely going to be an insert. And it doesn't matter. This if would always be true. Because if the cost is less than what was there, that means that I would be moving it forward in the thing. Is that true? No, that's not necessarily true. Just delete the Q, delete the colon. Yeah. Because I am using a new cost. I'm sorry, the heuristic for S prime will always be the same. It's just the cost to get to S prime that could be less. And here I've said, oh yes, the cost is definitely less. The thing is that S prime may have already been popped out of the queue. So I might have to put it back in the queue. Yeah. But either way, the new cost is lower. So just get rid of the colon. That's A-star search. It's pretty straightforward. The one thing it's not quite as beautiful theoretically as the uniform cost search. Because with uniform cost search, the first time we pop it off the queue, that is definitely the shortest route to it. With this, we have this heuristic, and there's certain properties on the heuristic that we need to have in order to have that same confidence. And I'm going to talk about that on Tuesday, not today. But the interesting part about this is about these search contours. When you're doing breadth first search and uniform cost search, things tend to go out in beautiful circles, searching everything with equal priority. It's just based on cost. How much does it cost to get there? With breadth first search, it's how many hops. On a uniform cost search, it's the cost of the hops. On greedy and A-star, same idea, but it will tend to search things that are closer to the goal if you have a reasonable heuristic. Okay, so this is the question. Will this algorithm always get us the cheapest one? That is, if we pop off the goal, is this always going to be the shortest? And the answer is if we have the proper type of heuristic. And we say they're admissible. I'll give you the heads up to that. You can look it up in the book if you want. Admissible heuristics tend to make it so that the first time it pops off the queue, it will be the shortest possible route. Yeah, question.
Uniform cost search, that one's guaranteed.
Well, okay, so the question is interesting. That is, with uniform cost search, you're guaranteed that the first time it pops off, it's going to be the shortest route. And so the question is, what if I did it first time with A star and got a route, and then just to double check that it's the shortest, I ran a uniform cost search to make sure that's the shortest. Is that a fair summary? Yeah, that would totally work. It's not going to save you any time, though. I guess the only place where that would be really useful is if you had a heuristic that was questionable, but tended to get you some solution real quick, and maybe you would use that if you would check it if you had time, but if you didn't, you just terminate the thing and throw it away. Yeah, that would work. Well, it's unlikely anybody would ever do it, but it would totally work. Other questions? Back there. Real loud. One more time.
Dijkstra. Let's take them all.
The next slide. Yeah, got it. Yes. So the greedy algorithm. So when I say the greedy here, yes, Dijkstra's is a greedy algorithm. I mean the best first algorithm here, the greedy algorithm that we talked about last time, not just any old greedy algorithm, which Dijkstra is indeed greedy. In general, the greedy is not the first thing that we find with the greedy algorithm is not necessarily to be the shortest route, but with Dijkstra's, it will always be the shortest route. Yeah. Yeah.
What happens if I don't care about cost or like this stuff? What happens if I just want any path?
Yeah, if you just want any path, the greedy is going to be the fastest to get you any old path. Yeah. Yeah. Say it again.
Does the same concept of like relaxing an edge hold the same A star? Because like in Dijkstra you can relax it if you know what's the optimal path.
I don't have a good answer for that. Let me get back to you. Yeah. Remind me. Would you send me an email? I'll have a good answer for you. Other questions? That is what I wanted to talk about today. We're getting closer to a midterm, so I hope you're spending some time reviewing everything. Really, the reason why we do things like the midterm is that we want you to go back and reflect on what you've learned, remind yourself. Spaced repetition and effortful recall tends to make it so that you actually retain things for more than just a short time. So there is a pedagogical reason besides just wanting to torture you. So I do appreciate you taking the time to do some reading and some reviewing. So have a good weekend, and I'll see you on Tuesday.